let's get real. What would happen if you were thrown into a black hole? This isn't science fiction, but speculation based on hardcore physics. Before we throw you in, let's briefly review what a black hole is. Albert Einstein once described a black hole as the place where God divides by zero, and he didn't believe it existed in the universe. But lo and behold, humans have actually discovered it, when extremely large and dense stars reach the end of their lives. They undergo a massive collapse, squeezing themselves to nothingness. The remaining core is called a singularity, a mysterious point in space-time with infinite density, resulting in infinite gravity. General relativity gave us a revolutionary idea. Gravity isn't a force acting on an object, it's simply the result of the curvature of space-time itself due to an object's mass. This theory perfectly explains how the Earth orbits the Sun, but there's no solid black surface inside a black hole. The singularity hidden deep within simply distorts space-time so much that it forms a deep well with vertical walls. Most amazing thing about black holes? It turns out that anything can become a black hole, whether you're a star, a planet, or even a tiny person like us. If you squeeze it into the right Schwarzschild radius, you can become a black hole. German physicist Karl Schwarzschild was the first to discover the exact solution to Einstein's field equations. A discovery both simple and beautiful. Take the Sun, for example. If all its mass were compressed into a sphere with a radius of just 3 kilometers, hey, it would become a black hole. What about the Earth? It would become a sphere with a radius of about 9 millimeters, about the size of a marble. As for humans, to become a black hole, you'd have to be squeezed down to something much smaller than a proton, incredibly small. But if you could shrink that much, you'd become a black hole too. So which black hole should you be thrown into? A small one? That's boring. One larger than the entire solar system with billions of solar masses? That might be too much. Let's choose a nearby Sagittarius A*****, the supermassive black hole at the center of the Milky Way. You, Earth, are orbiting it, and it's one of only 2 black holes ever imaged. Let's set the scene. Imagine you and I fly there and park our spaceship 1 trillion meters from the event horizon, the point of no return. I stay aboard and observe while you begin free fall toward the black hole. Here's a key point. General relativity tells us that people near a black hole experience time differently from others because the black hole distorts space-time so dramatically. The movie Interstellar demonstrates this effect. To keep track of time, I'll give you a special watch that simultaneously displays the elapsed time from your perspective and my perspective from the spaceship. Let's align our watches and your journey into the black hole officially begins. At the outset, you'll witness the distant black hole voraciously devouring matter. It's a spectacular sight. The intense friction heats the matter to incredibly high temperatures in reality. The accretion disk would appear bright blue or even white. Simulations often color it orange for easier visualization. When you first check your watch only, 30 minutes have passed and you've only covered 0.1% of the distance to the event horizon. So far, I've only gained 11 seconds on the spacecraft. Not a huge difference as you get closer to the black hole. The curvature of space-time around it is creating all sorts of bizarre visual effects. Light emanating from the side and even from behind is being gravitationally bent before it reaches your eyes. You've now been away for 2 hours and have covered 1.4% of the distance. On the spacecraft, I'm 44 seconds ahead of you. The black hole's shadow, the dark region in the center, seems to be growing faster than expected. This is gravitational lensing, bending light that would otherwise pass by you into your eyes. After a long pause, you check your watch again, and what you see is truly alarming. From your perspective, you left the spacecraft approximately 12 hours ago. But from my perspective on the spacecraft, I've been watching you drift toward the black hole for nearly 15.5 hours. We're getting very close to a black hole now, and things are about to get really weird. Before you reach the point of no return, you'll pass through a strange and amazing place, the photon sphere. If you were frozen in time at this moment and looked around, the sight would be astonishing. The photon sphere is one of the most bizarre places in the known universe. Here, gravity is perfectly balanced, allowing photons to orbit around the black hole, not light emitted or reflected by matter, but the photons themselves trapped in orbit. If a beam of light happens to be traveling tangentially to the black hole, it can orbit. But if the path deviates even slightly, the photon will either fall in or fly off into deep space. Under these very conditions, if you were frozen at the photon sphere and looked around, you would see your own reflection facing away from you. You would see multiple copies of the back of your head as if standing next to you, staring off into space. You're actually seeing yourself in real time without any technology required, simply because of the distortion of space-time itself. Beyond the photon sphere, you continue your descent, getting very close to the event horizon. The black hole takes up an increasingly larger portion of your field of view. It feels as if you're being swallowed by darkness. This is because the darkness distorts around you, revealing both the back and sides of the black hole's shadow, even parts that would normally be invisible to you in flat space-time. You've been gone for 13 hours, and in 24 minutes you'll cross the event horizon. But from the spacecraft, I've already observed your journey for nearly 20 hours. Another 18 minutes later, you check your watch again. Now I've been watching you from the ship for nearly 40 hours. What seemed to be the last 18 minutes for you lasted a full 18 hours for me. The final moment has arrived in 6 minutes. We'll cross the black hole's event horizon. You close your eyes, take a deep breath, and check your watch, but it seems broken. It shows that I've been watching you fall from the spacecraft for an infinite amount of time. But it's not broken. Such is the magic of physics. I spent decades, centuries aboard the spacecraft, watching you approach the event horizon infinitely slowly. Finally, I saw you redshift, meaning I'd need an infrared telescope to see you. I could never see you actually cross the event horizon even. If I lived forever, what felt like your last 6 minutes would last me an eternity aboard the spacecraft. It sounds like a fantasy, a pipe dream, but it's absolutely true. Straight out of Einstein's equations now, you're inside the event horizon. What happens inside a black hole? Strangely, you hardly notice the exact moment you cross the event horizon. You can still look out at the universe, see distant stars, and even see our spacecraft drifting through space. But all of this light, like you, is destined to head toward the singularity. You've passed the point of no return. And ahead lies the infinitely dense singularity, a place where the laws of physics we know break down and time seems to stand still. To escape the singularity's gravity, you need to travel faster than the speed of light, something we all know is impossible. A common misconception is that when you look outward, the intense time dilation effect will cause you to see the entire future history of the universe unfolding rapidly before your eyes. This isn't true. Due to the aberration effect, as you approach the singularity, you'll see the external universe compressed into an extremely thin ring of light. Eventually, when you're close enough, tidal forces kick in. Your feet will be stretched out in front of your body, and your entire body will be stretched out in a process called spaghettification. You and the black hole will become one, drifting together in the universe for eternity. Remember that in 1939, Einstein published a paper specifically declaring that the collapse of stars into singularities was implausible and impossible in the universe.